Hello my dear students, once again welcome to your physics online class. In this video we will be discussing about the current electricity, and in a reduced syllabus you have a very less to study about the current electricity, and moreover the chapter electromagnetism is completely omitted in your reduced syllabus. So here are the some points that we are going to discuss in today's video related to current electricity. First we will be discussing on the Ohms law, then we will be discussing on the ohmic conductor and the non-ohmic conductor. Third, we will also be discussing on the factors that affect the resistance. Then we will also learn the superconductor, a brief description about EMF, that is the electromotive force, and finally we will be learning how to find the equivalent resistance when the different resistances are connected either in series or in parallel. So coming to the first topic, the Ohm's law. So before we start with the Ohm's law, the three important terms which you must know are the first one being the current, and the second being the potential difference, and the third one being the resistance. Okay, so the current in physics it's denoted by I, the potential difference is denoted by V, and the resistance is denoted by R. Now what is current? So we know that whenever the electron flows through the conductor, it generates a electricity known as a current electricity, and the electricity due to these charges at rest are known as a static electricity, which we have already discussed in class 9 in a physical classroom as well. So here we will learn about the current electricity. So the rate of flow of charge is known as electricity. So I can write that I is defined as it is Q divided by T. Okay, so this expression tells us about the current. Current is the rate of flow of charge. So if n number of electrons are flowing and if E is the electronic charge, the same expression can be also written in the form I is equals to N E divided by T, where N is the number of electron flowing through the cross section of a wire per unit time and E is the electronic charge. So now coming to the unit of current, so we already know that the unit of charges is coulomb. So it is coulomb and the SI unit of time is second. So coulomb per second is the SI unit of time, which is also known as ampere. Okay, so ampere is the SI unit of current. So now coming to the second term, the potential difference. So what is a potential difference? So the potential difference is the work done in bringing a unit positive charge from an infinity to a given point. For example, if I have a charge Q here, okay, so this body is supposed to have a charge Q, and I have another test charge Q. What is a test charge now? The charge unity charge, a unit charge is known as a test charge. Now if you are asked to find the strength at A, which can also be called the potential at a point A, then what you must do, you must hold this charge and bring it here. Okay, so in that, if the work done is W and the displacement produced here is suppose S. Okay, so when we do apply a force and then change a displacement, then the work is done. So thus we can say that the potential difference is the work done in bringing a unit positive charge from an infinity to a given point. So the potential difference is the work done per unit charge. So therefore the potential difference generally given by V is equals to W divided by Q. Okay, so the potential difference is the work done per unit charge. So now coming to the unit of potential difference, the work is measured in terms of joule and the charge is measured in terms of coulomb. So joule per coulomb is the SI unit of potential difference, which is usually known as volt. Okay, so volt is the SI unit of potential difference. Now coming to the third term, the resistance. So the resistance is the resistive force offered to the flow of electrons when it passes through the conductor. Okay, so that resistive force is known as the resistance. Now what is this resistance caused due to? Because when we know that, suppose if this is a wire, Okay, through a wire, when the electron flows, what happens? It collides with the ion present there. Okay, and it also collides with one another. So that means when the electron flows through the wire, there is a collision occurring between the electron and the ions and the molecules of the given metals. So that obstruction offered is known as a resistance. So thus we can say that the resistance is the obstruction offered to the flow of current. Now coming to the topic Ohm's law. So what is the Ohm's law? The Ohm's law relate these three together. Okay, so the Ohm's law states that the current flowing through the conductor is directly proportional to the potential difference. The higher is the potential difference, the more will be the current flowing. So the Ohm's law, from the Ohm's law, what does it say? The Ohm's law says that the current flowing, that is I, is directly proportional to V. Okay, so that is the Ohm's law. Now what do? Now I take I to the denominator. Okay, so I directly proportional to V divided by I. Now to remove this proportionality sign, I introduce one constant R. Okay, so R directly proportional to V by I. Now if I cross multiply this expression, I will get V is equals to I into R. So this is the mathematical form of the Ohm's law, and where R is the resistance of a given conductor. So to define Ohm's law, you must state that the current flowing through the conductor is directly proportional to the potential difference maintained across its end, provided the resistance or the temperature remains constant. So now coming to the second one, ohmic and a non-ohmic conductor. So what is ohmic conductor? The ohmic conductor is the one that obeys the Ohm's law, and non-ohmic conductors are the one that do not obey the Ohm's law. Usually all the good conductors of electricity, they are ohmic conductor. By saying ohmic conductor, I also mean that in that conductor, the rate of flow of current is directly proportional to the potential difference. But in case of a non-ohmic conductor, such laws are not followed. So if I plot a graph for the ohmic conductor, if I plot V versus I graph, it will be a straight line passing through the origin. But in case of a non-ohmic conductor, it will be a curve which will not pass through the origin. So this is non-ohmic conductor and this one is the ohmic conductor. So that is the simple difference between the ohmic and the non-ohmic conductor. Ohmic conductor obeys the Ohm's law and its graph passes through the origin, and the graph will also be a straight line. But whereas the non-ohmic conductor is the one which does not obey the Ohm's law, and if the graph between V and I is plotted, it won't be a straight line and passing through the origin. Some of the examples of non-ohmic conductors are the diode, transistors, okay, semiconductors, they are the non-ohmic conductor. Now coming to the third topic, the factors affecting the resistance. Okay, so where is the resistance? The resistance comes from the Ohm's law, R. So resistance means it's the obstruction offered to the flow of the electrons. So if you have to travel a longer distance, there is a more chances of collision or accident. So similarly, if the length of the wire is greater enough, large, then the resistance will also be large. So the first factor is the resistance of the wire is directly proportional to the length. Now the second one, take for example, if you have to travel in a very narrow road, so there is a chances of a greater collision. But if you have to travel in a broader road, there is a less chances of collision. So the resistance, similarly, when the electron flows through the wire, if the wire is thick enough, the cross-sectional area of the wire being large, the resistance will be low. So the resistance is inversely proportional to the cross-sectional area A. Apart from this, the resistance of the conductor is also directly proportional to the temperature, because we know that with the increase in the temperature, the molecular motion, it increases. So what happens? When the motion increases, the chances of collision is also larger. Just like we see in a greater traffic area or the crowded places, what happens? The chances of accident is much more. So similarly, with the increase in temperature, what happens? The resistance of the conductor increases. Now if I combine both of these factors, then I will get R is directly proportional to L divided by A. Now again, to remove this proportionality sign, I introduce one constant, R is equals to rho L divided by A. Okay, so this, and from this, the name of this constant that I introduce is known as the specific resistance. Okay, so this is the specific resistance, or simply we can call resistivity. Okay, so this is the resistivity. Now coming to the another topic, the fourth, the superconductor. So now we know that the temperature, with the increase in the temperature, what happens? The resistance of the conductor, it increases. Now with the decrease in the temperature, what happens? The resistance of the conductor, it decreases. So certain conductors like the mercury, at a very low temperature, its resistivity is almost zero. So those types of conductor whose resistivity almost approaches the value 0 is known as a superconductor. Now coming to the fifth topic, EMF, that is the electromotive force. To understand this, I draw one cell. Okay, what is a cell now? The cell is a battery that contains the electrode and the electrolyte within it. Okay, so I simply draw one battery, a container. Okay, so where we have two of the electrodes, and then I have an electrolyte inside this battery, and then some external resistance is connected to this. Okay, so now what is the EMF? Now when no current is drawn from the cell, that means I do not connect any of the resistances to the external circuit, and when I measure a potential difference, that potential difference is said to be the EMF. That means when no current is drawn from the cell, the potential difference across its end is known as a EMF. There is also the other way of defining the EMF. So what is that? Suppose if I have a charge here, any charge Q. Okay, so now to move this charge around the external circuit and through the electrolyte, certain work is to be done. So therefore, the EMF can be defined as it is the amount of work done in moving a unit positive charge through the complete circuit. That means through the external circuit and as well as internal circuit. So therefore, epsilon. So this EMF is given by the symbol epsilon. Epsilon is equals to W divided by Q. Okay, where W is the work done in moving a unit positive charge through the internal circuit and as well as through the external circuit. Now coming to the sixth and the last topic of this session, the combination of resistances in series and as well as in parallel. For this you need to learn to derive the formula to find the equivalent resistance when they are connected either in parallel or in series. So now here I have drawn the two figures in which the three resistances, let's say R1, R2 and R3, they are connected in series, and another figure where I have connected the same resistances in parallel, let's say R1, R2 and R3, and both of them are connected to the battery with the potential difference V. Okay, so let the potential difference in both the cases be V. So getting the equivalent resistance means the total resistance of this circuit. Now let the current I passes. Okay, so remember that whenever the resistances are connected in series, the voltage across each of the resistance will be different, because each of the resistances are not connected individually to the battery. So let us say that the voltage across the first resistance be V1, okay, across the second be V2 and another be V3, and the current through each of them will be same since they are connected in series I. So now what do I do? So what is the total potential difference? It's V. So simply I can write that this V is divided into 3, V1 plus V2 plus V3. So now according to the Ohm's law, we have the formula V is equals to I into R. So what do I do? So I substitute that value. V means it is I into R. R is the current and R is the equivalent resistance. Now similarly, through the first resistance, the V will be equals to I into R1. Through the second, it will be I into R2, and for third, it will be I into R3. So I into R will be, now taking I common from all, I'll get R1 plus R2 plus R3. So I get cancelled. So therefore R will be equals to R1 plus R2 plus R3. Okay, so this is how we find the equivalent resistance when connected in series. So from this expression we see that the equivalent resistance of the resistances connected in series will simply be the algebraic sum of each of the resistance. Suppose if this is 2, 2 and 2. So, the total resistance of this circuit is simply going to be 2 plus 2 plus 2 is 6. Now, if there are n number of resistances, then the same formula R can be given as R1 plus R2 plus dot 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 up to Rn. Okay, so for n number of resistance. Now, coming to the next one, combination in parallel, always remember that since each of these resistances are connected separately to the terminal of the battery, so the voltage across each of them they remain same. But what is different here now? The current is different. So, let I1 flows through this one, I2 and I3 through the third resistance, okay, and the total current being I and the voltage being V. So, here the current is divided, okay, so the current I is divided into I1 plus I2 plus I3. Now, again what will I do? From the Ohm's law we have V is equals to I into R. So, therefore, I will be equals to V divided by R. So, substituting that value I for V by R, I will get the I1 will be V divided by R1 plus why V, because the voltage across each of them is same. So, V divided by R2 plus V divided by R3. Now, taking V common from all the sides on the right hand side, I will get V1 divided by R1 plus 1 divided by R2 plus 1 divided by R3. So, finally, V and V I can cancel. So, therefore, the inverse of the equivalent resistance 1 by R will be equals to 1 by R1 plus 1 by R2 plus 1 by R3. Okay, so, using this expression we can easily calculate the equivalent resistance of different resistances that is connected in parallel. Now, if there are n number of resistance, simply what can I do? I can go on adding the inverse of the resistance up to order n. So, this is how we get the equivalent resistance of the different resistances when connected either in series or in parallel. So, this is the end of this video current electricity. In the next video, we will be learning about the electric household circuit and also about the consumption of electric power in our houses. Thank you.